Okay, in the previous video, I introduced the basic structure of the probability, how to define a probability in a formal way, and and then I I gave you some basic concepts and how we can connect the structure to data, the structure of data. And here I'm going to give you a more detailed description of the structure underlying commonly used data. So first type of data we may be using in the future is the survey data. Survey is the most common experiment in social science. In social sciences, we cannot do perfect like the experiment like a natural science. We we cannot change, say, your I cannot change your wage to see its effect. I cannot change your income to see how your choice changes. I cannot change prices. So so all we can do is basically a survey, just asking questions to people. And it can be thought of as an experiment. As I said, it is an experiment. It survey is where the randomness is generated from. Because so the structure as an experiment is that first you randomly choose individuals. So that's where the randomness is generated. You have to ask a random person. Otherwise, if you, so for example, so typical mistake of many students is that they wanted to do their own survey. Okay, that's interesting. But the problem is when they survey, what they do is they ask their friends. They survey their friends. But your friends are not random people. They are they are similar to each other in some characteristics maybe, and or some students post their survey questions on their SNS like Instagram or like and some community internet community. Uh, the respondents are not random there either. So uh, in general, when I hear that a student would like to do a survey, then usually my answer is no. It's not uh, taking a survey is not an easy task. It takes a lot of resources, time, and more careful design. So it's not easy because that's where the randomness is generated. So it's that important. And then anyhow, the randomness is coming from choosing a person, and then from there it's easy. Just ask questions and record their answers. Their answer is the outcome, right? So so their answer is random in the sense that if you choose another random person, the answer will be different. In that sense, we understand their answers as uh, randomness. And some famous survey data you may be interested in, and like you may be using in your essays or in other courses, in your term papers. Uh, a panel study of income dynamics, PSID, is maybe one of the most popular research purpose data. And current population survey, national longitudinal survey of youth, health and retirement study, consumer expenditure survey, survey of consumer finances. You can see what they are about. Like some important variables, like a lot of studies are based on some of these data sets, and you see what they are about. So, if you are interested, if you wanna do real data work, I would be happy to help you. Like maybe not in this semester, but later in the future, um, I I can be of your help. So so please let me know if you're interested. So this is one of the most common types of data in social sciences and how we understand the structure of this data. What is the experiment and what is the randomness? Another important type of data is time series. So think about this. The probability of rain on Labor Day is 30%. Think about this sentence. This is 30%. So it's a clear, you know what it means. You understand it. So, and you also know that 30% is the probability. And the event is rain on Labor Day. Rain on Labor Day is a well-defined event, right? Then the problem here is, what is the underlying experiment for this probability? It's not clear what is the experiment you can repeat, and because to define a probability you have to repeat the experiment, but you cannot repeat anything here. You cannot leave Labor Day multiple times. So here still we have to define the probability. So we have to think about an experiment. That is, so we think of an hypothetical experiment. It's like this. There are, so think about it, it's a purely imaginary scenario. There are a lot of weather scenarios on Labor Day. And Mother Nature randomly chooses one scenario, right? And we think that every year on Labor Day is the repetitions. So Labor Day last year, Labor Day the year before, Labor Day the year before are repeated observations. So it's like the weather records on Labor Day are the data. If you take this as your random experiment, it's a little bit absurd. It's like so if you have a time machine, then you can leave, you can go to Labor Day and check the weather and come back and go to the Labor Day again, back and forth. If you can do that, that would be the random experiment, but that's even more absurd. So we have to think about a more realistic but still unrealistic experiment like this. So time series data are observations over time, and many economics analysis are based on time series analysis. For example, GDP. GDP. What is the GDP growth rate? What is the probability distribution of GDP growth rate next year? What is the probability that the stock market stock returns is higher than, let's say, 5% next year? You need to study that and you need to define the probability. So you need to have an experiment. So we think of an imaginary experiment, theoretical, for purely theoretical purpose, like this. So there are many scenarios in the economy, and some randomness chooses one scenario. So that's what you observe, and that is played every year. So the past is observations of that experiment. That's the underlying experiment in time series data. Okay, so far we discussed a very abstract structure and concepts. Now we are going directly to the data. Given the data, and we will study how to calculate probability, how to understand the probability. Here, think about this data. So this is the same example like rolling a dice, the simplest possible example. Suppose that you roll a dice 200 times and you recorded the outcome. So in experiment number 1, experiment number 2, experiment number 3, experiment number 200. And the first outcome was 1. Second outcome was 5, 4, 4, da, 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 da. So this is the full data, and it's a lot of information. But having a lot of information, it helps. It is helpful to conduct an accurate analysis, but it does not help when you present the information. So, like for example, suppose that I'm asking you, your boss is asking you, what is your outcomes from the experiment? Then would you say all the 200 outcomes? Of course not. Your boss expects you to summarize the data and like give you and give the boss a more compact and more meaningful information. So the data itself is not that much informative. It's just a huge array of numbers. So you have to summarize the data. And here in this example, here is how we summarize the data. So what is the outcome from the experiment? What did you get from the experiment? Then I would present this way. Just there are 6 possible outcomes. The sample space consists of 6 numbers, and for each value, you observe this many times. So we out of 200 observations, I observed 1 for 33 times, observed 2 for 31 times, and 3 for 32 times. This way, it summarizes very well. And it means, and here I defined frequency. Frequency is the number of occurrence for each outcome. So this outcome happened this many times. This outcome happened this many times. And sample size, again, is the number of repetitions. How many times you repeat the experiment. In this case, the sample size is 200 because you have repeated that many times. And of course, the sum of all the frequencies, must sum to the sample size, right? Otherwise, something is wrong. There is an error. So they must be the same by construction. And then to go one step further, you can define probability directly from the frequency distribution table. By the way, we call this table as the frequency distribution table. It shows how the frequencies are distributed across different outcomes. So frequency distribution table can be extended to a probability distribution table. It shows how the probability is distributed across different outcomes. And the probabilities are calculated as the ratio between the frequency over the sample size. So you observe 33 times out of 200, which is 16.5%. And similarly, like you observed 35 times out of 200. So the ratio is 17.5%. Again, the sum of all probabilities must be 100%. Obviously. Okay, this is how we calculate the probability from the data. Very intuitive, very simple, and exactly consistent with our structure and also consistent with what you thought, right? There is nothing new, but I would like to formulate everything into a unified structure. Unified structure will be maintained throughout this semester and throughout any fields of statistics. Okay, so I will stop here, and I will continue from this point in the next video. See you later.